Let's talk about a concept that is easy, but yet easy to get confused. So let's talk about weight versus mass. All right, it's important to know that weight is a force, and it represents the force of gravity acting on an object. Now, technically, the force of gravity is actually calculated using an equation like this: force of gravity equals some constant, and that's actually a known value, mass 1 times mass 2 divided by how far apart those masses are. And so the idea is, if we have two masses, M1 and M2, that these two masses attract each other, and they attract each other with a force that's equal to this equation. That's the force due to gravity. All right. So these two objects are trying to attract each other. All right. So that's the background in terms of what weight is. But what do we really do when we try to calculate weight? We stand on a scale. Oh, well, before I get into that part, mass is a measure of inertia. Okay, this is one of our parameters that we need to know. And up here, units for weight, we would say pounds if we're here in the US, but really it's a force unit. So we will always use newtons to represent our weight, our unit for the force due to gravity. Mass is a measure of inertia, and the units for inertia are kilograms. All right, so when we see kilograms, we should automatically think of that we're representing mass. When we see newtons, we're representing weight as a force. All right, mass is a measure of inertia, and it represents the resistance to change motion. Inertia, resistance to change. If something has very little mass, it's very easy to change the motion of that object. I think of a ping pong ball. A ping pong ball has very little mass. It takes very little force to change the motion of a ping pong ball. A bowling ball, however, is the other thing I think of when I think of something with a lot of inertia. A bowling ball has a lot of mass. It has a lot of resistance to change motion. It's hard to get it going and it's hard to stop it. Ping pong ball, easy to get it going, easy to stop it. So that inertia is quantified by measuring determining the object's mass, and we use units of kilograms to represent inertia. So weight is a force, inertia is resistance to change motion, and is quantified by mass of the object, which is units of kilograms. Let's explore this a little bit more. Let's say we wanted to measure the weight of an object. Well, what do? We take that object, if this is just a block that we're interested in, and we put it on a scale. Sorry, we put it on a scale. You stand on a bathroom scale to measure your weight. Well, when we do that, what forces are acting on this object? Well, we have the force due to gravity pulling the object downwards, and then we also have a force of the scale pushing up on the object. Okay, those are two forces acting on the object. And remember, we put those forces into this equation, m equals ma, and it's the center of mass, acceleration of the center of mass. Here's our m right here, and this is inertia. This is the object's resistance to change motion. And we know what a is, that's the acceleration of the object. In this case, if the object is sitting still, it's not moving on this scale, then A, acceleration, is 0, because the change in velocity over the change in time is going to be 0 meters per second squared. All right, well, let's keep that in mind here, and let's look at the forces acting on the object. We have the force due to gravity pulling down on the object, and we have the force due to the scale pushing up on the object. Pushing up. And remember, if we use our reference frame here, up is positive, then this is going to be a negative force, gravity, and this will be a positive force. And so now I can put these forces into this equation, F of scale, which is going to be positive, plus negative gravity is equal to MACOM. All right, well, that's pretty cool. Well, remember, when we stand on the bathroom scale, if we weigh something, we're actually looking at this number right here. So I'm just going to write this by itself, F scale equals MACOM plus F gravity. And here's the important part of this equation. As long as acceleration is 0, this part of the equation gets dropped out, and F scale equals F gravity. And therefore, we say the weight of the object is a positive number. That's just what we say, word on the street. We don't typically talk about, well, I weigh negative 185 pounds. I always say I weigh 180 pounds, 185, or whatever my weight is. And that's because this force and this force are going to add up to 0 as long as this object's not moving. If this object's moving, which we as humans do if we're standing on the scale and we move our arms, or if we squat down or stand up or whatever, if we move on the scale, this acceleration is no longer 0. And we need to account for that. But the force due to gravity is always going to be a constant number. That's the weight of the object. That's the force due to these two objects trying to attract each other. So that's a constant. But weight is a force. All right, so now let's look at this one layer deeper. And if I take that equation, I'll put it up here again, F scale equals MACOM plus F gravity. And I'll just emphasize this because A is 0, F scale equals F gravity. And that's how we weigh an object. So now, if we want to understand the object's mass, we take F gravity equals mg. This is our general equation for calculating gravity. And a lot of times you look up in a textbook, this is what, this is what it will, I kicked the wire. Let's try that again. This is a type of equation that you will see to calculate gravity. And then we calculate mass by dividing the force due to gravity by the acceleration due to gravity. And it's important here to know that we almost always will use gravity, the acceleration due to the force of gravity, as a negative value. This is the acceleration due to the force of gravity. And that's important. This is very important. This is not gravity. This is the acceleration due to the force of gravity. And then when we do that, when we take gravity as a negative force, which it will have, if we just put that object here, gravity is going to be pulling down on the object, and the scale is going to be pushing up on the object. So gravity is going to be a negative force. Acceleration due to the force of gravity is going to be a negative acceleration. Therefore, mass will be positive. Okay. Let me just check my notes here. Yeah. So a lot of times what we'll do is we'll calculate mass based upon a constant divisor of weight, and we'll say there's 4.4 newtons for every pound, things like that. So there's easy to do that because most of the time in the real world, the acceleration due to the force of gravity is negative 9.8 meters per second squared, but that's not always the case. If you go to different parts on the world, you can actually get a change in the acceleration due to the force of gravity by maybe as much as 1%. And that's because we go back to our original equation for gravity, and that's some constant, that's a gravitational constant, is the force of gravity is equal to the product of a constant times the product of two masses divided by how far apart those masses are from each other. Again, it looks something like this. Okay, this is the distance between the two objects, the center masses of the two objects. And we can calculate the force of gravity, either one of these forces, these are going to be equal and opposite to each other, using this equation, a gravitational constant times the mass of one object times the mass of the other object and how far apart they are squared. And that actually gives us the force of gravity. So you can think about if you're on a part of the Earth that is further from the center of mass than another part. So maybe we're on Mount Everest versus our desert out here. I'm drawing a blank. If your elevation is extremely different, we may actually get a different R between the center of the Earth. Oh, I'm doing a bad job. I guess I could have drawn the Earth and then a person standing on the Earth. And these would be the two masses that are in this equation. Me as a very small mass, and the mass of the Earth very large. But if I'm at a different point on the Earth, like maybe a peak of Everest versus Death Valley is what I was trying to think of, maybe I can get as much of a 1% difference in how far the two masses are, and my weight is actually different at different parts of the Earth. But for all practical purposes, in terms of problems that we deal with, the weight of the person is a constant because that R squared really does not change that much when we're doing things like running or jumping or biking or swimming in different parts of even the US or national, or most of the part international. Okay, so the force of gravity is nearly constant, but it is a function of how far apart the two masses are from each other. Okay, I hope that helps. Weight is a force. Mass is a measure of an object's inertia. Mass is a scalar. Weight is a vector. As magnitude and direction, mass is only a magnitude. And it's going to be the same regardless of if we're on different objects. These masses will always be the same. And the force of gravity will be, these masses will always be the same. The force of gravity will be a function of how far apart those two objects are from each other. Okay, I hope that helps. Thanks so much.